Now we will talk about soft margins, which is an extension of the current formulation, because in the current formulation, SVMs remains a linear discriminant. And as such, with non-linearly separable data, there are no valid solutions that can be obtained by quadratic programming. And as such, if we put in there some non-linearable data, and using this formulation that we see so far, the solver will just bring us that there are no feasible solutions. It is not possible to achieve a solution where with an accuracy of 100%. So to relax the problem and to make it solvable, even though we are dealing with non-linearly separable data, we are introducing slack variables. So these slacks variable are in fact a C value, which is positive or 0 for each data xt. So if we have a xt which is equal to 0, there's no problem with the xt variable. It is correctly classified. It is not in the margin. If we have a c that is higher than 0, we are deviating. We have a deviation of the xt variable from the margin. It means that if the value is between 0 and 1, the data is correctly classified, but it is within the margin. So it is on the right side, but in the margin. If the value of C is higher than 1, it means that we are misclassified. The data is not well classified. So it is on the other side of the hyperplane in terms of correct classification. So for doing this, we are rewriting the SVM optimization criterion. We are getting with a new criterion where, you know, the previous version was without this thing here. So now we are adding 1 minus ct, which gives us some capacity to tolerate data in the margin or directly misclassified. So to allow this kind of tolerance, or this is kind of a way to tolerate some errors, we will also compute the error associated to the margins, which is basically to sum the value of ct. So we are summing the ct as a measure to say how much tolerance we have, or how many, or by how much we have data in the margin. So if we look at this problem here, we have a problem where we are dealing with two classes again, the blue squares, the red circles, and we see that the circle values like this one, that one, and that one, they are data in the margin. These are data with an alpha that is greater than 0. So these are non-zero, and all the others here, like these data instances, are not supervectors. These are data with a 0 value alpha. For those who are support vectors, we also have the cases where we have a C value. So we can see here that over the 5 support vectors, this one, that one, and that one are correctly classified and are not in the margin. So their C is equal to 0. While this case here is a case where the C is between 0 and 1. So it is a data that is correctly classified, but in the margin, and so because the margin is that region here. While the other case here, we have data that is an instance that is misclassified. It is not well classified. It is on the wrong side of the hyperplane. And in such case, the C is more than 1. So we have a primal formulation with soft margins. We have this thing here. So we are getting back to the primal formulation. The difference is that we are adding this thing and that thing and that thing here. So we have 3 elements that are added to the original formulation. The original formulation was basically this with that, not excluding that thing. And yes, this is the original primal formulation. So the difference here is like the mu. The mu t here are the Lagrange multipliers used to enforce the constraint that the C are positive or equal to 0. It is to be sure that we don't get negative C values. This is the same thing that we had before with the alpha. we also have the C penalty. So this thing includes a C factor. This factor is a way to regularize. So this is weighting between having things correctly classified versus having a penalty that correspond to the amount of data that have a non-zero C. So the quantity of instances, the number of instances, and by how much they are in the margin. So the sum of the CT. So this C penalty factor allows us to get different types of classifiers. With a C equal to 0, we are kind of allowing to get all data in the margin. It's not good because basically we will ignore somehow the C. With a C that is higher, we will put more emphasis on the C, and so we will aim at reducing the number of instances with C that are non-zero. So if we fall back on developing with the same approach we had before, I'm just skipping the developments because it's basically based on the same principle. So if we get from the primal formulation to the dual formulation with soft margins, we get that thing here. So it's pretty much the same in terms of maximization. We aim at maximizing the same equation. The difference is with the constraints. In fact, this is like we had before, but this is different in the sense that we are bounding the alpha t according to C. So the C penalty here is giving us a maximum value. So previously, if we had a really big alpha value for a given instance, here it will be bounded at C, and we will have in fact a slack value for that. So we will not get alphas that are bigger than C in general. So that C penalty is somehow adjusting the amount of saturation over the alpha, and so the amount also then of samples with some non-zero C value.